It's recording. Great. So I had to reset my password, which means my internet doesn't work anymore. It's really annoying, but whatever. I'm using the hotspot on my phone. Hopefully, well, it's like, I don't know. I don't know what I have. I don't know. Yeah, exactly. Yeah, I think my billing cycle just started, so I think I'm okay. It's like, I don't know. We'll see. I'll keep you guys posted. Okay. Oh, this is just trying to name these. Okay, so of course, if you don't have the chapter 4 notes, probably come grab them because we're going to be using them today. And I also brought the chapter 3 notes, chapter 2 notes, chapter 3 notes. I'll put them here, or 4 notes, sorry. And if you don't have your test back yet, I have those as well. Oh yeah, you bet. Put these things here. Okay. Cool. Oh yeah. They're sorted alphabetically by last name. Okay. So today we're going to finish chapter 4, which on the schedule we were supposed to spend another day on it, but I think because I typed up the notes, we're just kind of churning through all this a lot faster, mostly because we would have had to write all this out. So we'll see what we do with this extra day. Probably just steamroll ahead, but whatever. Okay, so just as a quick review, right, last day we talked about hypothesis testing. I feel like last day was a sleepy day for all of us, myself included. So you just review it. Don't worry, you'll have a chance to prove what you're made of on the assignment on question 2. You have to do a hypothesis test. But just as a quick run through, right, we talked about there's 4 steps that we're going to follow for hypothesis testing, regardless of the type of question that we're analyzing. As soon as you have to do a hypothesis test, you have to follow these 4 steps, right? So the first step is you have to state your null and alternative hypothesis, right? What's your idea about what's going to happen? Step 2 is do the test, right? We're going to start and we calculate z-scores, and then we'll move into t-scores, but they do the same thing, right? How far is your sample mean from your hypothesized mean? Step 3, we find the p-value. The p-value is essentially just the area in the tail, right? And so we did an example together, or maybe not together, I don't know. But we did an example, and I showed you that you actually know how to do the test and find the p-value already. We just haven't called them that, right? And then step 4 is where you pull it all together, right? You use the p-value to draw your conclusion. Do you have enough evidence to reject H naught, or do you not have enough evidence to reject H naught? Right? And we said, well, if the p-value is small enough, right, smaller than some alpha level, right, then we have enough evidence to reject H naught. Okay? And to bring that point home, oh, it's all laggy. I'll blame my phone. We have this little guy. Snoop. that's really laggy. So we did a whole example. It took basically half the class, so we can't go through it and do another example. But while you're still kind of awake and with me, I'll show you. Not that you're falling asleep in this class, but maybe it's after lunch, middle of the week. So if you go on your Moodle, I posted all these practice problems, and I haven't really been pushing you to go to the practice problems until now. Okay? The practice problems for chapter 4 are really solid. Okay, so the ones before it is kind of like, oh, things change and what I focus on changes. But for chapter 4, 5, and 6, and 7, things don't really change. So what I've done is I've just looked through a ton of different textbooks, pulled out questions that I think are good for you to practice, type them up. I've also given you a list of questions from the textbook. Oh, there's a textbook? Well, sort of, but not really. It's on Moodle, right? Just in case you want to have some practice going through. I think all of these are multiple choice with the solutions in the back. So if you wanted to do those, but I'd say as far as like where you should be focusing would be these ones that I've typed up. Okay. And I've also typed up the solutions and they're on Moodle. I'm not perfect. So some of the solutions, there might be typos in there. I don't know. Chapter 4 should be pretty good, but I know there's a typo somewhere. I'll say that I haven't tackled. But now you know. So there's chapter 4 practice questions. So when you're doing the assignment, right, you can find a problem that's like it in like practice questions, look at the solutions, reverse engineer it. That's how I work, at least. I know for some reason people don't like it when students do that. I don't know. It's the only way I learn. Looking at the solution and being like, oh, okay, I get it. Reverse engineer it. So, any questions about hypothesis testing? Okay. So what we covered last day, I'll be calling formal hypothesis testing. What we said was there's two main streams of inference. Inference is, right, when we take sample information to learn something or to infer something about the population, right? And so there's two main streams of doing that. First one is hypothesis testing, this kind of formal approach of all these 4 steps that we have to do. The next one is confidence intervals, which are way more fun and I dare say easier. So that's what we're doing today. February 27th. Yowzas. I keep thinking it's January still. Ooh. I mean, it's good, but also, eek. So, hypothesis testing, just to go back to that, and to make the connection kind of, hypothesis testing is when we want to know if something is significantly less than or significantly greater than or significantly different from some value, right? But even if we decide that, yeah, this is less than some value, right? We found the mean odor threshold for wine tasters was significantly less than the odor threshold for the general population or something like that. It doesn't tell us what the odor threshold might be for wine tasters, right? It just says, no, it's less than the general population. There you go, right? And so confidence intervals give us a range of plausible values where the population mean might be. Right? And so we do this, we use confidence intervals kind of intuitively, right? If I asked you, how far is it from me to the door? I'm terrible at distances, so I don't know. 6 meters? I don't know. I I don't know. That's my best guess, right? So from me to the door, 6 meters. That's my guess. Okay? That would correspond to my sample mean, right? My sample mean is my best guess at what the population mean might be, right? And so what I would say, I wouldn't say, oh, from me to the door, it's 6 meters, done, right? Because I'm not 100% sure, I have no idea. I would say 6 meters plus or minus 2 meters, because I'm really not that sure, right? A pretty big interval. And we kind of know this intuitively, right? Oh, 6 meters plus or minus 2 meters. Fair enough. Somewhere in that range, I've captured the actual distance to the door, right? And then you might say, well, how sure are you? I'll say 95% sure, 99% sure, right? And that's going to depend on the width of my interval, right? So confidence intervals work the exact same way. So we've got our best guess, which is the sample mean, right? And then we build up this kind of plus minus buffer zone, right? And so let's just talk about what's in this formula here, because everything kind of looks familiar. Okay. Right. X bar, we know is the sample mean. The only thing we haven't seen before is the Z star, but we did see it briefly, right? We saw it in the t-table. So we've seen it just ever so briefly before. You got your tables, right? Because it's so laggy, I won't pull them up here. Just quicker to show you on here. If you wanted to make a 95% confidence interval, for example, you'd go to 95% confidence level here, and then down third row from the bottom, you've got a Z star row. And so that's where you're going to pull this Z star. Z star is called your critical value. So let's say here, Z star is a critical value found using the t-table. Oh. Writing hunched over isn't helping. Oh well. Get it. It's also typed up, but sometimes it's nice to have the extra notes. Okay. So that's the only new thing that we don't know what it is in this calculation, right? Because we know sigma is the population standard deviation and n is the sample size, right? And so we've also been calling sigma over root n, that's your standard error. Standard error. Oops. I'll take it up with TELUS. So, okay. Together, right, so we've got this critical value, we've got the standard error, right? Together, this whole plus minus chunk is called the margin of error. Okay? And so, how do I show that? I'll do it over here. I moved over to the side. What is it? Is it closed captioning? Like, she moved the slide over. X bar plus minus Z star times sigma over root n. This section here, Z star times sigma over root n, is called the margin of error. So you've got this margin of error on your estimate. So here's your estimate. What you'll see here, right, later on, I've already foreshadowed that we're actually going to be moving away from Z's and into T's, right? So what we saw before was that the only difference between a Z and a T is that instead of having the population standard deviation, we now have the sample standard deviation, right? So notice that the confidence interval for a T situation is basically the same, right? We've got our estimate plus or minus T star, which is also a critical value, right? Critical value just like the Z star, and we actually find it the same. And then instead of sigma, we have S in terms of calculations. Okay? All right. So, scared to move over here. There. So I've got these things all typed up, but let's do some practice finding these Z stars because, I don't know, we haven't done it before. Well, just once. I've got a little blurb there telling you how to do it in words, but it's just easier to show you, right? And so if we want, so for example, what's the Z star of a 90% confidence interval? Confidence interval, I call it CI. Seems reasonable. Confidential informant. No. Z star for a 90% confidence interval, right? You're going to go to 90%, and then you're going to go down to the Z star line, which is the second to last or third to last line, 1.645. Z star for a 95% confidence interval, 1.960. And finally, Z star for a 99% confidence interval. You want to be careful with all of those because there's 98, 99, 99.5, 99.8, and 99.9. So you want to make sure that you pick the right one. So 99% confidence interval, 2.576. So what the confidence interval is doing is it's just capturing the central, whatever percentage of data that you want to look at, right? If you want to build a 90% confidence interval, it'll capture the central 90%, right? 95, central 95%, etc. So I've got it down here, right? From the 68, 95, 99.7 rule, right? We know that if we want a 95% confidence interval, right, the central 95%, we would do plus or minus 2 standard deviations. Right? This is the same, because what we're doing, I'll do this one because it's cleaner. Here, we're not talking standard deviations anymore because we're talking about a mean observation, right? So we're not moving out just the standard deviation. For means, we have to move out a standard error instead, right? Sigma over root n. But what we're saying is we want to do plus or minus 2 standard errors from your sample mean, right? So it's the same idea, right? But now because we have this more precise 1.96, we're going to use that instead. But I think we can all agree 1.96 is basically 2. 2's really close to 1.96, right? So, but from now on, for these confidence intervals, you're going to use the the Z stars from the table. But just know that you've seen it before. When you calculate your interval, right? What did I say? 6 meters plus or minus 2 meters? Is that what I said? Let's say that's what I said. Right? I'm going to get an interval, right? 6 minus 2, 4 to 6 plus 2, 8. Right? So my interval then is from 4 to 8. Now I can say I'm 95% confident that the interval from 4 to 8 meters captures the actual distance to the door. Right? So we have the same situation with our calculation, right? We're going to get a lower bound and an upper bound. Okay? For notation, and it's important that we use the right notation, okay? We're going to write these in round brackets, okay? And you're going to have your lower bound. In my case, is 4 meters. Right? 4, yeah, 4 meters, comma, 8 meters. So my lower bound and my upper bound, and then close it with a round bracket. Right? So that's the notation that I'll be expecting to see. Right? Lower bound to the upper bound. So why would we use 95%? In fact, 95% is a default. It's kind of the default confidence level. Okay? And the reason for that is because we need this kind of balance between being really confident, right, and precision. For example, if I told you that, okay, I'm 100% confident that the distance to the door is between 0 and 15 meters. I can be 100% confident, but it doesn't actually tell you anything about the distance to the door, right? And so we have this trade-off of, okay, we say 95%, that's still really high. We can still be, confident in these results, right? But also it lets us have these kind of tighter bounds, right, for more precise estimates, right? So that we're not just putting out garbage with these huge bounds on it, right? So, so 95% is the default, of course, because this is a testing thing, right? I'll say make a 90% confidence interval, make a 98% confidence interval, right? But in industry, and if you're reading any sort of research paper, they will probably be using a 95% confidence interval, just because that's pretty standard. Okay? So, unless they want to hide something, then you could conveniently make a 90% confidence interval or a 99% confidence interval. Kind of mess around with it that way. Okay? Let's scroll. One thing I want to add to these notes here on page 8, so we use 95% confidence intervals as a default. Right? Thinking back to hypothesis testing, we said as a default we do a two-sided test, right? So if you're not sure, you're going to do a two-sided test, which means you have the not equal to sign in the alternative hypothesis, but also you're going to use an alpha level of 0.05. Okay? These two are directly related, so all the defaults are all related. And what I want to add here with a two-sided alpha level of 0.05. I'll show you what I mean. And you'll need this for the assignment for 2B. Yeah, for question 2B, you'll need that. So listen up. Okay. If we draw the normal distribution, And we start with the alpha level. The alpha level is the area in the tail, right? If the area in the tail is less than 0.05, you can reject the null hypothesis, right? And so if you have a two-sided test, remember, that means that this area has to be split between both of the tails, right? So the default is 0.025 here and 0.025 here. So this is the default two-sided alpha level of 0.05. 0.05 has to be split evenly amongst the tails. So now you've got 0.025 in both the tails. Which is the same as saying you've captured between this point and this point, you captured the central 95%, right, or 0.95. So that's how they're related. Default confidence level. On the assignment, right, I've told you to, this kind of the sneaky part, right, once you have the confidence interval that you need, then smooth sailing. But I've told you, okay, you have a one-sided p-value of 0.05, so not a two-sided anymore. So that means you have to have 0.05 in one of the tails, right? But because of how intervals, these confidence intervals work, if you have to have 0.05 in one tail, you have to have 0.05 in the other tail as well, right? So now instead of 0.025 and 0.025, now you have 0.05 and 0.05. So what am I actually asking for? I'm asking for a 90% confidence interval. Jot that down. You'll need it. Or I guess it's in the notes. So that's for 2B on the assignment. So when we're doing these confidence intervals, what you'll find is that the math isn't that bad. Right? We just kind of plug in our values, find this interval. That's only half the work. Okay? The other half of the work is going to be interpreting these values. Okay? There's a lot of ways that you could go through and misinterpret these. And one thing that you have to keep in mind, trying to figure out what it might be, it's fixed, right? So it's not moving around. We just don't know what it is, right? So our sample mean, however, moves around, right? Our sample mean is what we build our confidence interval around, right? And so that's why we're only 95% confident, for example, right? Because we don't know if our sample was good, if it's capturing the population mean or not, right? But the important part, the most important part, is that this population mean, it's fixed, right? So we just don't know what it is, right? And so I strongly suggest that you just use this sentence structure. Right? I'll be using this sentence structure. It's just something, until you get in the habit of maybe tweaking it a little bit, I don't really think you can tweak it that much without saying something incorrectly. Okay? So stick to this, memorize it. Hate to say that, but it helps. Sometimes it helps. So we are 95% confident, for example, that the interval from 4 to 8, right, the interval that you found, captures the population mean of whatever I asked you to make an interval of, right? Mean distance to the door. Doesn't really make sense, but in the questions, it'll make more sense. And so here, right, we're 95% confident that the interval from this to this, here's the keyword that it captures the population mean. And then you just, here we're talking about the population mean, right? Later on, we'll be talking about the population mean difference, the population difference in means. We'll be talking about the population proportion, right? So we'll be talking about a lot of different parameters, right? But the sentence structure stays the same, right? So as soon as you've made an interval, a confidence interval, you're going to interpret it with this little blurb. So, any questions before we do the example? Okay. So here, I've just copied the previous example. There we go. It's the wine taster one. I know it's not that fun, but whatever. At least we know the numbers and we're kind of familiar with the question. Saves us some time. So then at the end, I've asked you to construct a 95% confidence interval for the mean odor threshold of all wine tasters. All wine tasters is the population, right? So the population of wine tasters. Okay. All right, nothing to it but to do it. Let's see here. I'll add a page. Oh yeah. What example is this? I gotta pull it out so I don't have to scroll around so much. So, example 5. We're given some information, right? And this is from before. So we're given that sigma is 7, n is 30, right? Our sample size is 30, and our sample mean was 21.5. We want to make a 95% confidence interval. So what I'm going to do is I'm going to write down Z star for a 95% confidence interval is 1.960. And I'll just say from T-table beside it. So you don't have to do any sort of blurb there. Pardon? The X bar is your sample mean. So 21.5 is your sample mean. But then the hypothesized mean was 25. Here's the thing though. Instead of scrolling because it can't handle it, X bar plus or minus Z star times sigma over root n is what we're trying to solve for, right? Here, the only reason I didn't write down the mu is because we don't need it. And in fact, this sample mean is for the wine tasters, right? So now, in the hypothesis test, we decided that, okay, the mean odor threshold for wine tasters is less than 25. Right? So now we're trying to figure out, okay, if it's less than 25, well, what is it? Right? Is it between 10 and 12 or something else, right? And so that's what we're trying to figure out here. So for what's nice about confidence intervals is you don't have to know the mean, right? The population mean, the hypothesized mean. You don't have to have any of that. We just need the sample information. Okay? Does that? Yeah. So, well, we can just plug in these values, right? And so we're going to plug in these values 21.5 plus minus z star, which is 1.960, times sigma, which is 7, over the square root of 30. We're just plugging in those values. I'm going to show all my steps. You don't have to. One thing that I do want you to do, though, is keep all your decimals until the very end. And on the test, I'll tell you how many decimal places I want. Unless it's money, then, of course, you just do 2 decimal places at the end, right? But I'll give you the number of decimal places. In this case, I haven't told you how many decimal places to use. So a good rule of thumb is, well, this is the information that I've given you in the question, right? And so you just match however many the largest number of decimal places I gave you was, right? Here I gave you 1 decimal place, 0 decimal places, 0 decimal places. So we have to give our answer to 1 decimal place. Right? That's a pretty good rule of thumb, is you just match however many decimal places I gave you. Right? So, but like I said, if it matters, I'll tell you how many decimal places to use. Okay? So here we go. 7 divided by the square root of 30. So I've got plus minus, keep the 1.960 for now, times 1.27801931. Keep the 21.5 up there. Now I can multiply that by 1.96. And if you skipped straight to this part, that's fine. Well, I mean, skip that one step. Plus or minus 2.50491783. This is our margin of error, right? The 2.5049 whatever, that's your margin of error. I'll make a little note here. Margin of error. So now you have a store button on your calculator. If you don't know how to use it, or if you're not sure if you do, you can ask me after class. But I'm going to store this just so I can keep all my decimal places, right? Because I don't want to round something too early. 21.5 minus 2.5, whatever. I'm going to write out all my decimals just to show where everything came from. But if you skip to the rounded answer right away, that's fine too. I get 18.99508217 up to 21.5 plus that guy. 24.00491783. You're going to keep all your decimal places until the very, very end. Right? Now we can round to 1 decimal place. So I get 19.0 to 24.0. I'm putting the 0.0 because 19 is not the same as 19.0, right? I know, weird, but it's not. Okay. So, and notice, right, round brackets, lower bound, comma, upper bound, and round bracket, of course. So now it's time to interpret this confidence interval. All right. We'll start with, we built a 95% confidence interval, so we're 95% confident the interval from 19.0 to 24.0 captures population mean, where is it? So if you reread the question, right, which I would show you on there, but too slow, construct a 95% confidence interval for the mean odor threshold of all wine tasters. Right? And so it captures the mean odor threshold of all wine tasters. In our kind of default interpretation, right, we said captures the population mean. Here we've got the mean, here we've got all wine tasters, so we are talking about the population mean. Any questions about that? So in general, I think people like confidence intervals better than hypothesis testing, but there's a but. We can do hypothesis testing using confidence intervals. Okay? The reason for that is because we already looked at the relationship between the alpha level and a confidence interval. Okay? And so by the same logic, right, if we're 95% confident that the population mean for wine tasters is between 19 and 24, both of those are below the hypothesized mean of 25, right? If you bring back that hypothesis that mu is 25, well, both of these, I'm 95% confident that everything is below 25. Right? So by that same logic, I can reject the null hypothesis, right? And say, well, I'm 95% confident that the mean is less than 25. So that's kind of neat. We can use confidence intervals to do hypothesis testing. Recall, and HA was that mu is less than 25. Gets a little sticky because we have a one-sided test and a confidence, but it doesn't matter. Since the 95% confidence interval is consistently below the hypothesized mean of 25, is consistently below, and I'll put in brackets, well, more brackets, I guess, 19.0 to 24.0, just to emphasize that both of those are below the hypothesized mean of 25, which means we have enough evidence to reject the null hypothesis in favor of the alternative, right? Because 19 to 24 is all below 25. So we have enough evidence to reject H naught in favor of HA. So again, we can conclude the mean odor threshold for wine tasters, bless you, is significantly lower than the general population. Just tying it back to that hypothesis test that we did last day. Oof. Any questions about that? Keep that up for a little bit. So for a situation like this, it's not as relevant as when we get into proportions, okay? But usually we want to know, okay, how big of a sample do I need to collect in order to, for example, reduce my margin of error to some value, right? So I require some precision for my estimate. How big of a sample size do I need to get that? So for this situation, what I'm getting at is the last section, calculating the required sample size. Not really that relevant for real life stuff for this one, but just because we do it and it is relevant for proportions later on, I want to show you that we can do it in both scenarios, right? And so what we're going to do is I'm going to show you how to calculate some required sample size. Okay? So let's scroll down here, or up, I guess. There. So given sigma, so you have to know sigma, which is not really that reasonable, which we'll get to later, but given sigma and some desired confidence level, so you want to have a 95% confidence level or a 90% confidence level, right, which translates to a Z star, right? Say I want a 95% confidence interval, Z star is 1.96. And margin of error, which we're going to denote by a lowercase m. All the textbooks have different notation. Could be capital M-E, capital M, lowercase o, capital E, lowercase m. Doesn't matter. They're all the margin of error. It's that plus minus chunk. So if you have some desired margin of error, then we can calculate the sample size. I'll just show you quickly how we get there so it's not so crazy. or shouldn't say calculating, solving for n if we have a confidence interval, x bar plus minus z star times sigma over root n, remember this section, oh, secret section, there you go, is the margin of error. Yeah. So what we can do then is we can say, okay, well, then m is z star times sigma over the square root of n. I'll clean that up a bit. If we have to solve for n here, we're going to multiply both sides by the square root of n. So you have m times the square root of n is z star times sigma. Trying to get n on its own, we have to divide both sides by m. Square root of n is z star times sigma over m. Ditching the square root, we have to square both sides. So z star times sigma over m, all to the power of 2. That's on your formula sheet, but that's how you get it. On formula sheet. So then, if you look at example 6, if we want to decrease our margin of error to plus or minus 2, remember in the example that we just did, our margin of error was 2.5. So even though it's not clear, I'm referring to the previous example. Oh yeah, so our margin of error was 2.5. Right? So we want to decrease the margin of error to 2. With a confidence level of 95% again, and of course sigma is still 7. So how many wine tasters do we need to sample in order to bring that margin of error down? So example 6. Recall our margin of error was, oh, I wonder if it's still, no. I'm gonna steal it so I don't have to memorize it. Was 2.5. Oh my goodness. What happened? We keep up. Well, it'll take a while. I'll just keep going. There. It's going, it's going. I think we're there. Roughly 2.5. 2.50491783. Roughly 2.5. We want to know, or we want to solve for n, solve for the n that makes the margin of error plus minus 2. So we can just use the formula. Oh, yeah. N is Z star times sigma over M to the power of 2, or all squared. Z star is still 1.96, right? Because we still want to do a 95% confidence interval. So 1.960 times sigma, which is 7, divided by M. This has to be our desired margin of error. Oh. 1.96 times 7 divided by 2, oops, is 6.86 squared, which is 47.0596. One thing is that it's really, really difficult to only sample 0.0596 of a wine taster, right? / impossible. So, but the other thing is that if we only did 47, our margin of error, just because of how the N behaves in our equation, remember N is in the denominator, so we have to increase. Because of how the N works, 47, our margin of error would be slightly bigger than 2. Right? Our goal was 2, no more. And so for these sample size calculations, you have to round up to the nearest whole value. Right? So in our case, we would have to sample 48 wine tasters to get our margin of error down. And it would actually be less than 2, but that's good. Right? And so since we can't sample 0.0596 of a wine taster, we must round up, oops, to the nearest whole value. We would need to sample 48 wine tasters. Before you get too excited, there's just one little note that I want to add about decision errors. But any questions about this before I do? Oh. 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 No. So in hypothesis testing especially, right, there's always a chance that we're wrong, right? So we've rejected the null hypothesis because the p-value was so small, right? But we have to be aware that there are these decision errors that we could be making. For example, what if I rejected the null hypothesis when I shouldn't have, right? Or what if I didn't reject it when I should have rejected it, right? Those are errors that we could make, and we don't know if we're making them, right? But they have names, and so that's what I'm going to introduce you to now, but that's about it. So here comes a section on decision errors, which I'll just make a note here, not in printout. On printout? I don't know. add it later, but for now, for you guys, this is what you have. So like I said, in hypothesis testing, there's always a chance that we're making the wrong decision. So in hypothesis testing, oops, in hypothesis testing, there is always a chance that we have made a decision error, a chance that we have made a decision error. Usually how these things are presented is in a table. So I'm going to draw the table for you. Here, I'll start with the test conclusion. So whatever conclusion you've made from your data, you can either do not reject H0, or you reject H0. Those are your two options for what you did in your hypothesis testing. On the other hand, H0 is true or H0 is false. We don't know. Oh, what the? Wait, it doesn't do that. Okay. I'll just put truth on this side. We don't know if H0 is true or if H0 is false. If we did, we wouldn't have to do any testing, right? But somewhere in the background, there is a population mean. So that's what's going to determine if H0 is true or false. If H0 is true and you don't reject H0, that's okay, right? That's not an error. That's good, right? So here you're okay. If H0 is true, but you decided to reject H0, that would be a type 1 error, is what it's called. So this is a type 1 error. The type 1 error, or the probability of a type 1 error, is the p-value, right? The p-value is the probability that the null hypothesis is true, right? If you think of it that way. So then the type 1 error happens with a probability of the p-value, right? So you did reject H0, but there's a chance that you were wrong, right? So I'll just write that down below here. The p-value is the probability of making a type 1 error. Moving on, if H0 is false, meaning you should have rejected it, but you decide not to, we call that a type 2 error. So this is a type 2 error. Of course, there are ways to quantify the probability of making a type 2 error, but it's way beyond the scope of this course. So p-value is fine. We've seen those. We can handle those, right? Type 2 error is a different beast. So just know that that's what it is. And then, of course, if H0 is false and you rejected it, then you're okay. Right? You didn't make an error. Any questions? So I do want to make a note because I kind of pulled a fast one on you guys. Assignment 4 is due on Monday. I usually give you a week, but it's just a quickie. And also, if you want, you can stay behind and work on this, but otherwise, we are done for today. I'll stick around if you have questions about the assignment, but otherwise, we're done chapter 4.